So when we talk about transaction concepts and techniques, usually we want to use a real system. We want to see the implementation, right? Because that will make the discussions more practical. Therefore, I have chosen SQL Server as the system we will be using for our transaction discussion. And this SQL Server is available both on premises or on our private network and in Azure as well, or in a cloud. First, a common question is, what is a transaction, right? So a transaction is just a sequence of operation, a sequence of tasks, which are performed in a single, okay, the keyword is single logical unit of work. A transaction is a single logical unit of work. So think about transferring money from your savings to your checking, right? For that transaction, for that work, there are two steps. You will need to withdraw money from your savings account and then put the money in your checking account. So these two steps are two operations, and these two operations are contained in a single logical unit of work. They must either succeed together or they must fail together. We cannot have one succeeded, the other failed. Okay, so that's the concept of transaction. Transactions have four very important properties. ACID, atomicity. This simply means all your data modifications, all the changes will be committed, will be saved, or none of them will be saved. Okay, so all or nothing. Consistency, meaning transactions must bring the database or the data from one consistent state to the next. Remember, all or nothing, right? Isolation simply means when a transaction is doing work, it will go through several steps, and the results of the intermediate steps cannot be seen by other concurrent transactions. So think about our money transfer, our money transfer transaction, right? There are two steps. If that transaction is still taking place, the intermediate state, for example, money has been withdrawn from your savings account, $2,000, but has not been put in your checking account. The transaction is still going, then concurrent transactions cannot see the balance of your savings account because the transaction is still going on. So that's the intermediate results, intermediate state. So isolation simply means the transaction is like a black box. Before the transaction is complete, the internal state of the transaction shouldn't be visible. Durability means once a transaction is complete, then all the changes will be made to the database and cannot be lost. Okay, so just so simple, ACID. And in order to maintain the data integrity and the data consistency, we usually implement measures to protect our data when the data is being changed. Locking is commonly used. Row versioning is also commonly used. So let's look at them in a little bit more details. So they are both used to protect our data. Locking will lock the data which is being updated, being changed. So other concurrent transactions or concurrent users cannot use the data. So that's locking. There are different types of locks. Row versioning simply means the database engine will take a copy of the data. We call that copy a snapshot. We'll take a snapshot of the data. And when the data is being changed, if there is a read operation, the read operations can read the snapshot. When there's a problem with the data change, the database engine needs to roll back, then the database engine can roll back to the snapshot. Okay, a snapshot is just like a copy of the data at a very specific moment. So row versioning and the locking both are commonly used for protecting our data. So usually we use locking in an environment in which we have a lot of data changes, and we use row versioning in an environment in which most operations are read-only operations. We may have some data changes, but not a whole lot. If we do not protect our data, when the data is being changed, then we will have concurrency problems. Okay, so when people talk about concurrency problems, usually they are talking about these problems. We have loss updates, meaning the last update will override previous updates, and then transactions who have made previous updates may not be even aware of their changes have been overwritten. So it's a big problem. Okay, uncommitted dependency, just 30 read. So think about our money transfer operation, right? Before that transaction is complete, if we allow other concurrent transactions to read the account balance of our savings account, then that may not be accurate. The balance may not be accurate because that transaction might be aborted. The change might be rolled back, right? So we call those scenarios a dirty read. Inconsistent analysis, or we call that non-repeatable read, meaning a concurrent transaction may read a piece of data several times, 2-3 times, but each and every time the value is different. The value is different. So the reason why this is happening is we do not isolate a transaction. Okay, and then the last one, Fenton reads. So Fenton reads usually are caused by inserts and deletes. So if we do not isolate a transaction, we let other concurrent transactions see the intermediate state of a transaction, meaning before the transaction is complete, we let other transactions see the intermediate results of that transaction. Then other concurrent transactions may see a record, but later they run the same query, they will not see that record. For example, the same query is run twice, maybe just milliseconds apart. The first time, a record was seen. The second time, the record disappeared because we don't isolate transaction. We do not isolate a transaction, and that transaction might have deleted that record, right? Wrote back or whatever. So we call that phantom reads, like we all know. You see something now, but you don't see it later. It's like, you know, you saw a ghost, right? So those are common concurrency problems. We have two types of concurrency, pessimistic and optimistic. So pessimistic and optimistic, let's just think about these two words as English words. Pessimistic means you are worried, right? You know, there are problems, you don't do something to, like, you know, you are worried there may be problems. If you do not do something to avoid the problems, then the problems will occur. So that's the meaning of pessimistic. Pessimistic concurrency control is usually used in an environment where you have a lot of data changes, a transactional environment. And when we implement the pessimistic concurrency control, we use locks. So locks is more restrictive. The other type of concurrency control is optimistic. So you think about the English word optimistic, right? Optimistic meaning we are feeling good. So life is good. We don't need to worry about data integrity problems. So we just let each user, each transaction do their work. If there's a problem, we will fix the problem. So usually in a reporting environment, most of the operations are read-only operations. Therefore, we can feel optimistic because rarely we change the database content. We're just running our queries. We read data for creating reports. But when we need to update the database content, we still want to make sure we don't have any conflict, right? If there's a conflict, then we need to roll back the change. But generally speaking, we're not that much worried. So we call this optimistic concurrency control. If there's a problem, we will roll back using the snapshot. So when we do optimistic concurrency control, we use snapshots for rolling back. And this is also a very common concept about transaction processing or about locking. So lock granularity and hierarchies. The concept is if you lock up just a record, because usually when we change the data, we change a record, right? Or, you know, if there are several records, you just lock up those records. If we just lock up the data, we have to lock up because the data is being changed. We have small granularity, so to speak. Then we can allow other data to be used. We can allow other data to be used by other transactions, other users, right? So we can increase the concurrency, the throughput of our system, of our database, if we have a very small lock granularity. We just lock up the data we must lock up very small granularity. The problem is that in a busy environment, we have so many concurrent users and the concurrent transactions. If we just have very small lock granularity, we just lock up the records which are being updated, are being changed, then there will be a lot of locks. And there is an overhead for the database management system to maintain the locks. So when the overhead is so high, then performance of the database management system degrades. So that's the problem. So if we have small log granularity, the overhead is high, though concurrency is increased. But when we reach a point, the overhead is so high, and then the performance of the database management system has decreased. We need to do something about that, right? So usually we do a log escalation, or we try to lock up data in larger granularity. So larger granularities will decrease the maintenance overhead. So in a database environment on a database server, usually we have logs at different levels. For example, if you are working on the entire table, you will lock up the entire table. If you are just updating a record, you lock up that specific record. So we have logs at different levels of the data hierarchy. We call that log hierarchies. And we have different types of logs here. So you can just read through them. And this is a very common interview question. Log escalation. Okay, so meaning you have small log granularities, but the overhead has become so high, and the database management system is hard to keep up with the overhead. The performance has degraded. Then the database management system will escalate the log, meaning will go with a larger log granularity. Instead of just locking up one record, it might lock up a bunch of records. It might lock up the entire table, okay, depending on the situation. So log escalation will decrease the overhead. It will also decrease the concurrency or the throughput of the database management system. But ideally, it will decrease the overhead, though it may decrease concurrency, but the throughput will increase, or at least stay the same, right? And deadlock, this is a very common problem, and this is for real. So when we say there's a deadlock, meaning we have two or maybe several transactions going on at the same time. Each transaction is waiting for a resource locked by other concurrent transactions. For example, we have 3 transactions, A, B, C. They all need resources 1, 2, 3. So A has locked up 1, and the A is waiting for 2 and 3. And the B has locked up 2, and B is waiting for 1 and 3. C has locked up 3 and is waiting for 1 and 2. But they will not release their respective locks until they are done, right? So they will keep holding on the resource they have locked up and waiting for other resources to be released by other concurrent transactions, and other concurrent transactions will not release their resources either because they are waiting for other resources to complete. So that's what we mean by a deadlock. And usually a deadlock is resolved by the database management system. We don't need to worry about resolving or breaking up a deadlock. The database management system will take care of that. But based on my experience, in a busy environment, very often a deadlock will require operator intervention because the database management system is so busy, the environment is so busy, and the database management system is not responsive enough. Therefore, deadlocks exist longer than normal. When that happens, your your application, your database, your environment may freeze up. Okay, I've seen this at Microsoft, at some other large environments as well. When that happens, we will just need to break, how do I say that? Terminate, right? Terminate a transaction involved in a deadlock so other transactions can proceed. And the transaction that we have chosen to terminate, we call that a victim of a deadlock. And this is a very, very common. Okay, so I've seen this so many times at large places. Microsoft has said, Starbucks and many other places. Usually, we don't need to worry about deadlocks because the database management system will handle that. But in a busy environment, the database engine gets so much behind. If we do not do something, your application, your database may freeze up. And that's a very big problem. So we just need to investigate the issue, find one of those transactions, and then terminate that. And we call that transaction that we terminate a victim. And there are ways that we can use to avoid deadlocks. So for developers, in your code, if you have several transactions needing the same resources to complete, you want to make sure in your code you lock up or you require the resources in the same order. For example, if in your code you have 3 different operations which may require 3 different resources to complete 3 different transactions requiring the same 3 resources, you want to have your code require and lock up the resources in the same order. For example, resource 1, 2, 3, right? All of them will request and lock up resources 1 first, 2 next, 3 last. Okay, so resource 1, resource 2, resource 3. If you have one operation requesting 1 first, locking up 1 first, the other operation requesting 3 first and then locking up 3, then that will increase the possibility of having a deadlock. And other best practices are just common sense. We want our transactions to be as quick, as brief as possible. So in a transaction, you will put the steps you absolutely must include in the transaction. And you do not want to require user input in a transaction because user may pause, right? If a user is pausing, then your transaction is being paused as well. And that will lock up the resources. And that will significantly decrease concurrency and then will decrease the throughput of your application, your system, your database. And then the last practice is use a lower isolation level. That depends on your business requirements. Okay, so we just need to use the isolation level we need to use. Don't go with something which you don't need. That's what I'm saying. Okay. And nowadays, we have more powerful, more sophisticated hardware. If we have a bunch of CPUs, a very powerful environment, powerful hardware, the database management systems can do lock partitioning, meaning a lock can be partitioned and each partition can be handled by a CPU or by some specific piece of hardware, and that will improve the query performance. And this is something done automatically by the database management system. We cannot configure it, okay? And if you want to know more about what we just went over, follow this link. There is a lot of additional details